Okay, so what I'm going to start off this video by is showing you the information that I get from the SQA. I'm going to make this available on the Teams so you've got access to it whenever you like. It is the first part of this video you can actually skip, so I'll give a wee timestamp in the little information description box below to where you can skip to if you don't want to see this part, but I think it's going to be quite useful for a lot of you. So if we scroll down, we can take a look at the contents. Really, all this is guff, 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 and then we get to some important stuff. So the first bit really is just guff for teachers, still guff for teachers, and this is where we get to what you guys need to know. Now, because we can't do any actual reactions or practicals, experiments, we've skipped rates of reaction, which hopefully we'll get a chance to come back to later on. Now, if we keep scrolling, we get to this bit, and this is really where I want to start off by speaking to you about this stuff. So, a lot of teachers, me included, have taken to giving out lists of I'm good at this, I'm bad at this, checklists if you know things. I actually think it's much better if you guys are taught how to make those lists by yourself and how to do them well, even from quite tricky formats like this. So, the first little bit is elements in the periodic table are arranged in order of increasing atomic number, aka, do you know that hydrogen has one proton? And let's think, what can I actually remember off the top of my head that's quite a big one? Organonesium, right at the end, has 118. Now, you don't need to remember every single one of the elements. You just need to be able to use the periodic table to determine how many protons, neutrons, or electrons any given element has. And the next little bit is the periodic table can be used to determine whether an element is a metal or a non-metal. So if you think back to that lesson where I showed you the data booklet, and I've got the data booklet here, and scroll down, and we've got our little staircase, So everything on this side of the staircase is a non-metal, all of this stuff is a metal, and hydrogen's weird. So once again, all of these metals, these non-metals, and hydrogen's weird, usually classified as a non-metal. However, under some circumstances it can behave a little bit like a metal. It's a bit of a weird one. Right, so very quickly what I want to do is show you what I would do on Word to build myself a checklist as the course is progressing. Now, what I would say is that taking notes in the first instance, I think, is good. It helps in some way process the information. However, it's not the end of that learning process, and what you'll find is you will forget a lot of the stuff that you understand and you understood. However, the more times that you go over it, the more you build an understanding of it, and the more times you do it in a different way, the better your understanding will be of it. So building your notes, copying notes from the lessons, that's really the first step. The second step is doing little questions and seeing if you can deal with the information in a way that you have to provide an answer to a given question. The next way is probably doing this. So this is me condensing all of that information into a checklist and a spreadsheet type format with notes attached to it. So I'm going to go to this little tab here on Word, and I can find a table, and I'm just going to drag that table down. Now 8 is going to be way too few, however I can keep adding those lines to the table as we go. So the syntax, or the way that teachers have been taught how to speak, is like learning intention. I don't personally, that doesn't really work for me, and not that I can spell. I like to go with learning point for myself, because that is the point, the very specific little bit. So in the next column, what I might have is my notes for that particular thing. So from here, I would be looking at the notes that I'd taken from the video, and then I'd be condensing them, so making them a lot smaller. I'll zoom in so you can see that a little bit better. So that you can condense those notes into your own words. Now, I can't emphasize enough how important that actually is. The processing of the information into your own language is very, very important. And I'll put in helpful links in the third column. So in the third column, what I could do is I could link in things from BBC Bitesize, little bits and pieces that I think to myself, when I'm revising, I might want to come back to this and use it again. Or even something you didn't quite get the whole way through, but you want to come back to. So, where I've got my learning points, where are we? The first little bit is elements in the periodic table are arranged in order of increasing atomic number. So I can change that into right. So in my notes, I might want to put a nuclide notation. So for example, and I will use nitrogen in this example. Now, there's probably a way to do this. I don't know how to do it. So what I'm going to do is just do it a little bit clunky, like this, and N. So there is no charge, so this is an atom. The atomic number is 7, and the mass number is 14. So 14 minus 7 equals 7. So there are 7 neutrons in nitrogen. So that's me put my learning, that's me taking the quite clunky information from here, or quite frankly, the lessons that you're getting. And I've converted it into a learning point, which is what teachers call learning intentions. I am going to do this as we go along, and when we finish Unit 1, I'm going to have completed this and done the helpful links. Now, you can simply use that at the end. However, the thing that I would emphasise is that if you do it yourself, you will be better at it. And you will understand the information better, you will remember it better. So taking the time, putting in the effort, really does have a positive impact on your final grade at the end of the year. I can make it as easy as I like. I can have all of this put up and I can just give it to you in that format. I do think that my job is to make the chemistry as straightforward as possible. Or maybe not even as straightforward, that's probably the wrong way of saying it, but certainly as accessible as possible, and present it in a way that is good to listen to, that is clear and straightforward. However, the thing that I think a lot of pupils have been missing over the years is the effort that you go into producing your own notes and your own lists and your own, basically your own revision material. And by the end of the year, you will have some revision material to use. So hopefully this was a little bit helpful. What I'm going to do just now is go through the bits that we have done, and then we will start the lesson properly. So, groups are columns in the periodic table containing elements with the same number of outer electrons indicated by the group number, and you should be able to use the data booklet and down here to see that group 3 has 3 outer electrons, group 2 has 2, group 1 has 1, group 4 has 4, group 5 has 5, group 6 has 6, group 7 has 7, and group 0 has 8. And remembering that the valency is all about filling your outer shell. So the valency for carbon is 4 because it needs 4 bonds, aka it needs 4 extra electrons to get up to 8, which would be a full shell. However, oxygen has a valency of 2 because it's got 6. Elements within a group share the same valency and similar chemical properties because they have the same number of electrons in their outer energy levels. So we will actually dive into this a little bit further when we do the reactions. So we've kind of covered it, kind of not. It's a bit half and half. We will come back to it when we do the reactions. The electron arrangement of the first 20 elements can be written. Not remembered, written. So you've got to get up to, and I think I said we've got to get up to calcium in the periodic table in that lesson. Like I said, they haven't often gone up to calcium. They usually stop at argon, but you do need to be able to use up to calcium. So you don't need to worry about jumping over to gallium. You would just stop there. They wouldn't be able to ask you any questions further than that. Atom has a nucleus containing protons, neutrons, and electrons that orbit the nucleus. So that was our Rutherford experiment that we saw me draw out. Protons have a charge of 1 positive, neutrons are neutral, and electrons have a charge of 1 negative. You should know that. Protons and neutrons have an approximate mass of 1 atomic mass unit, and electrons have no mass. Now, we haven't really spoken about that too much yet, and basically this comes back to this little part here. So this little bit being to know that the atomic number is 7, and you can take 7 away from 14 to find out how many neutrons you've got, because each proton has a mass of 1 and each neutron has a mass of 1 as well. The number of protons in an atom is given by the atomic number. That's your nuclide notation bit that we covered. In a neutral atom, the numbers of electrons is equal to the number of protons. It is only ever an atom when this is true. So we have covered the mass number of an atom. We've covered that. We have very quickly covered isotopes. We have covered nuclide notations, but we'll be playing with them a little bit more later on. This bit here we have not done. I wonder if I can change. I don't appear to be able to change the colour of that. I'm going to leave that blank because actually we've not really looked at this a huge amount. We will look at that at some point. We've definitely done covalent bonding. We've done all the shapes, and we have done double and triple covalent bonds. We will come back to them later. We have not done covalent networks yet. So, and we've not really done this bit yet, which we will get onto today. Covalent network structures we will do today as well, and we'll talk a little bit about that when we bring it all together. We've done ionic compounds in terms of the metals lose and the non-metals gain. We have not done ion-electron equations yet. Yes, we've spoken about that. We could probably do with speaking about that a little bit more. We've done that. We've not done this, which we will probably get onto today. Haven't done that, and haven't done that. That's fine. And we've done the naming. We have done the naming. And we've done the valence rules. And we haven't done that yet. So we've done good little bits and pieces of things so far. So this is all the stuff that we've covered. The bits that I haven't highlighted, we will be covering. I don't teach it in strictly the order that it comes up in here, which is why it is good to be building your own learning points as you go along. It's useful and it's helpful, and it will build your understanding. Okay, so the picture we're looking at is a salt crystal. That is not one that I've created, that's one from Wikipedia. However, I'm going to show you a very quick time lapse of that I did this morning, showing salt crystal formation from dissolved salt, and then I'm going to show you some pictures of those salt crystals down a microscope. So once we've done that, we'll do the ion-electron equations, which you need to take the notes for, and the metallic bonding, which you need to take the notes for. Apart from that, there's no other associated work with this lesson. We're going to do this lesson, and next lesson will be a bit and piecey, and we're going to bring together a couple of things that we've done, and then we will have a big task next week that I will set out for you. It's basically going to be a poster that you can do to kind of bring all the main parts of the identification of bonding together. Okay, so this is our crystal surface down a microscope. If I move it around a little bit, we should be able to see, hopefully, the little bit of crust that we got from the time lapse. And if I can focus that a little bit better, we can see a little bit of a crystal structure there. What I'm going to try and do is give us a slightly closer view of that. It's not perfect, but I think you should be able to see, certainly. There we go. That we've got the salt has come out of solution and formed. Ooh. There we go. Cube-like crystals when they've formed properly. So that should hopefully give us a couple of images to look at. And we can see that that's a little bit of an unusual surface that we've got there. Back to the camera. So this is what our salt crystal looks like. There we go. There are some slightly nicer looking crystals. And we can see that those have formed little cubes there. And I'll take a little, try and take a photo of. This is really what I'm wanting to look at here, which is the formation of that crystal. And we've got some nice crystals forming there as well. Now the crystals aren't particularly large because I use a hairdryer to speed up the evaporation of the water, which has made the crystals a little drier than they would otherwise have been. There's some, that's actually quite a nice one. You can get that focused. So that little square there is a crystal, and we can see that just there. I'll put these pictures up. I don't think I can clear up the image much more on this particular microscope. That's about as good as we're gonna get, unfortunately, unless I can find something else. You can see the crust there. That's where it dried fastest, actually. Let's see if I can change the lighting. Oh, the lighting being changed does have a little bit of an impact. Try and go for that lighting. So the crystals on the very outside are much smaller because they dried faster, and then we've got some of these. Let's see if I can find some of those slightly better crystals again. The crystals on the inside. Ooh, that's not a bad sized one there actually. So I want to get to the outside edge where it really dried a little slower. Still on the outside crust there. There we go. So those crystals dried quite slowly and they formed nice cubes. This is actually due to the actual arrangement of the ions in the crystal lattice structure. So this picture here that we've got is a salt crystal, a properly formed salt crystal, and it's got the sodium and chlorine ions all side by side, and so this is how our crystals form. The slower they form, the better, really. or the bigger they will be. It's why when you see those really big lava crystals, they have formed very, very slowly from the cooling process. So that's our square little crystals there, and that was just from dehydrating some salty water. Okay, so we've got to cover these ion-electron equations. Now, the ion part just means that we'll be dealing with an ion. Ion somewhere along the way, and we'll be dealing with an electron somewhere along the way as well. Now, the sodium itself will start off as a solid metallic compound, and that sodium will kick out an electron. So as it kicks out an electron, it's probably going to be in an aqueous state at this point. It's going to gain a positive charge, and that electron has to be on this side of the equation. Every equation must have whatever's on the left-hand side must equal what's on the right-hand side. So if I just put up here, there is no charge on that sodium, so there's 0 charge. Then that equals, well, we've got a positive charge there of 1. If we want to get that to 0, we need to add a charge of -1, and our electron's got that charge of -1. So that's basically 1 plus 1 negative equals 0. Now, what we're going to do next is we're going to take a little look at the chlorine. Now, the chlorine is diatomic, means that in its natural state, you're only ever going to find it as Cl2, and that will be a gas. Now, when we add in our electrons, we're going to produce 2 Cl negative ions in an aqueous state. Now, that means that I'm going to need to plop in 2 electrons here. And so this chlorine in its diatomic state plus 2 electrons gives us 2 Cl negative. But how many electrons did I actually get out of the sodium? Well, I only got 1. So to give me 2, I need to start off with 2 sodium atoms. That will give me 2 sodium ions, and then that will give me 2 electrons there. Those 2 electrons then go into our chlorine, producing our chlorine ions. So now I've essentially got, if I give this that colour, and I'll make the sodium blue. I'll have these positive ions, which will want to be surrounded by negative ions. And that will form our crystal lattice, and that would be the salt crystals you saw just beforehand, and they formed when the water evaporated and the crystal lattice structure appeared, and that they formed, hopefully, I'm not sure how well it turned out, but hopefully you saw that we got cubes essentially of salt forming, and they kind of maybe looked a little bit like that. And we had a couple of really good ones. Most of them were formed a little bit too quickly, so they were a little bit too small. But that is your ion-electron equation. So, if you are asked in the exam to draw out the ion, say you were given the question, write the ion equation for the formation of magnesium ions. Now, the first thing I would do is check my data booklet, and I would see that magnesium's in group 2, which means it's going to be losing 2 electrons to form its ion. So I'm going to start off with magnesium solid. Now, that's our state symbol. We'll come on to those a lot more when we do the equations later on. But that's my solid magnesium. I'm going to get Mg, and it's probably going to be aqueous, 2 positive plus 2E negative. And those are my 2 electrons coming off there, and my magnesium 2 positive ion. So if you were asked to write out the ion electron equation, that's how you would do it, and you would need to include the state symbols as well. Take a look at where the usually a metal, take a look at what group it's in. That'll tell you what the charge on the ion should be. If it was in group 3, it would be a 3 positive ion. We'll do questions like this later on as well. Okay, so at this point we have covered the basics of ionic bonding, and we've also covered our covalent molecules. We will come back to covalent bonding again, but I want to finish off with our third distinct type of bonding, which is metallic bonding, and this is the type of bonding you find in metals. So it's very important that you describe this using the wording that the SQA likes. So metal atoms are held together by the attraction of these delocalized electrons for the protons in the metal nuclei. So when you travel from class to class, you're delocalized. You are not stationary in any location. And this is really what's happening with these electrons. They are able to move from one atom to the next. And the force of attraction between these atoms is really the movement of these delocalized electrons between each atom, keeping the entire structure together. It gives metals some really distinctive properties that make them very, very useful. And we'll go into those properties a little bit later on, because the big end round off of all of this will be how to determine what type of bonding you actually have given any given material. And so this is gonna come back again when we cover that and when we do the task near the end. But this is metallic bonding, and that's your third type of bonding. We do need to bring this all together and clear it up slightly, but if you make sure you have your covalent bonding and your 4 different covalent molecules, your linear, your angular, trigonal, pyramidal, and tetrahedral, you've got your ionic bonding with your ionic lattice, and finally you've got metals with your metallic bonding. If you've got all of those notes to this point, you're good. You've kept with it. So what we're going to go on to next really is to take a look at some experiments, and these are going to show you, hopefully, if I don't electrocute myself, the conductivity in different materials, and we'll talk a little bit about them. But this lesson's been a bit bitty. It's mainly because I needed to cover metallic bonding. I like covering it now. It does come up again, and the ion electron equations. So admittedly, this lesson's a bit bits and pieces that we've needed to just cover, but that is it for today. No tasks either, by the way. No tasks for this one. We'll have a big task next week, and I'll put that up later on.